Hello everyone and welcome to EAPG Pathshala. I am Dr. Roshan Livingston, working as a medical physicist in the Department of Radiology, Christian Medical College, Vellore. The module which you are going to learn today is on mammography. This module comes under the topic radiation biophysics. What does it mammography means? Mammography is a study that uses low energy X-rays for imaging the breast for diagnosis and screening. Mammography also requires images of the highest quality to visualize low contrast visible mass and calcifications, which may be about 100 microns in size. Here we see an image where there are a lot of small dots which are visualized. There are about 5 pairs of dots in that image. However, some are not visualized. The best quality of mammography system would show up all the patterns that are seen in this phantom. However, it is also required to keep radiation doses as low as possible because breast is a radiation sensitive organ and there is a risk of carcinogenesis associated with the X-ray technique. So what is the basic objective of the study? To understand the working principle of a mammographic equipment, to understand different detectors used in mammographic imaging. What are the components of the mammography machine? You can see that's an illustration of the various components as shown in the figure. There's an X-ray tube, high frequency generator, compression device, anti-scatter grid, image detector, automatic exposure control. This is the bigger view of the mammographic machine, which is inner part of the mammography machine. X-ray tube. The X-ray tube of a mammography machine is fixed, but as seen, it is actually tilted. It has a rotating anode X-ray tube with molybdenum or rhodium as the target material. Generally, in conventional fluoroscopy machine, it has tungsten, but in mammography machine, it has molybdenum or rhodium. Currently, for tomosynthesis procedures, some of the companies manufacture tungsten target because of high heat loading. The X-ray tube potential for imaging the soft tissue ranges from 20 to 35 kilovoltage depending on the thickness of the breast. Molybdenum target is used for smaller breast thickness. For breast thickness above 6 centimeter, rhodium target can be selected. Then we have the filter. The use of filter is to enhance contrast sensitivity. Molybdenum target uses a molybdenum filter which attenuates the bremsstrahlung spectrum above the energy of 20 kilo electron volt. This is usually used for smaller breast sizes. Rhodium filter attenuates energy of 23.2 keV used for thicker and dense breast sizes. Hence we see here there are two energy levels. For lower energy levels such as 20 keV, molybdenum can be used. For higher energy levels such as 23.2 and above, rhodium can be used. Here, to have a proper imaging, we need fine focus or a broad focus. Hence, the focal spot is very crucial for imaging a breast tissue. The fine focus is usually 0.1 millimeter. Broad focus, it is 0.3 millimeter. Focal spots are generally small to reduce blurring and enables to see small calcification of the order of about 100 microns. Fine focus spot is generally used for magnification technique. There is also a high voltage generator near DC high voltage waveform with minimal ripple can be used. The tube voltage should be accurate to about plus or minus 1 kilovolt. The tube current should be about 100 mA or greater on large focus and 50 mA or greater on fine focus. There is also a compression device. What is the potential benefit of a compression device? It gives uniform breast thickness, reduces the blurring from patient motion, reduces scatter radiation and improves contrast sensitivity. It also reduces radiation dose. It also allows better visualization of tissues which are close to the chest wall. There is also an anti-scatter grid. In case of mammography, low ratio grids are used. The material which is used for lead strips, in between the lead strips, are low X-ray absorption material. It has stationary grid or a moving grid. In case of a stationary grid, it has high line density, example 80 lines per centimeter, and an aluminum interspace material. In case of moving grid, with about 30 lines per centimeter, there is paper or some cotton fiber interspace. Then we move on to automatic exposure control, as seen in that image. Automatic exposure control sensor, which is placed just under the film cassette or a CR cassette or the detector. What is this automatic exposure control? The automatic exposure control automatically selects the exposure parameter depending on the thickness and density of the breast tissue. It also has the circuit which automatically cuts off the radiation once the predetermined value for creating a good image is reached. The cutting off is done using relays, just as we find in automatic exposure control's digital radiography system. Let us go on to the image detectors. Traditionally, film screen receptors were used. Later on, we move on to digital detectors. There are various types of digital detectors that can be used in mammography. The various detectors are computer radiography, slot scan acquisition CCD array based device, indirect conversion with scintillation and a thin film transistor, direct conversion and a thin film transistor. These are various digital detectors. Let us move on slowly towards film screen receptor. Generally, single-sided emulsion coated films are used for mammography purpose. The cassettes that are used for mammography purpose have single-sided intensifying screen with an absorptive base. The films can be identified with a notch on the right hand side of the film, as seen in this illustration. The advantage of film screen receptor is that it has high spatial resolution. What is spatial resolution? Spatial resolution is the ability to distinguish between two different objects separately. Hence, for a film screen receptor, the spatial resolution is about 20 line pairs per millimeter to demonstrate fine speculations and microcalcifications. It can also provide high contrast details, allows visualization of subtle differences among soft tissue densities. In case of these film screen receptors, when we use automatic exposure control, the dense part of the breast is positioned near the sensor in order to give uniform density to the film. And overexposure may lead to film darkening. Mammography systems are tuned with films supplied by different vendors. Hence, the AEC sensors are sensitive to various types of films. Next, we move on to digital mammographic detectors. These kind of detectors are used currently in various hospitals. As the kind of film screen radiography is getting outdated, we are slowly moving into computer radiography or direct digital radiography devices. The function of digital mammographic detector overcomes the film screen limitations by adopting optimized image processing algorithms with wide exposure latitude and contrast resolution. Increased efficiency and patient flow is possible with digital mammography detectors. It also enhances image quality, and there are a lot of options available in digital mammography which are not available in a film screen combination. When we see this image, we see the response curve of a film and a digital detector. We see the film's characteristic curve as well as the wider latitude in a digital radiography system. The exposure and optical density are independent in a digital detector. Let's look into a computed radiography system. Computed radiography uses computed radiography cassette, which can replace the film screen cassette. It can also be used as a retrofit. The existing mammography systems, which were using film screen combination, we can use the same cassettes, which are from CR, into the slot provided for the film screen mammography system. In a CR system, barium fluorobromide doped with europium 2+ is used as a phosphor material. The cassette based PSP detector directly replaces a direct screen film receptor. In a CR cassette, when incident X-ray photons interacting with the phosphor creates electrons which are trapped in the phosphor material to form a latent image. The CR reader uses the laser which stimulates the trapped electrons to fall to a ground state by releasing energy in the form of light. The light that is emitting out is blue in color. That blue light that is emitted from the phosphor screen is absorbed by a photomultiplier tube which converts light into electrical signal. This signal is then amplified and processed to be displayed on a monitor. Hence, for mammography purpose, we need high resolution CR cassettes. Hence, the packing factor for the phosphor which is used for CR should be very high. The image resolution we are considering for mammography is about 100 microns. Hence, CR readers come with 100 micron pixel size. In a dual side reading CR reader, the resolution can go up to 50 microns. It is very good for image quality. The cost of these CR readers are less than flat panel detectors. Next, we move on to a slot scan imaging system which is used for mammography. The figure illustrates the slot scan mammography system. What are the various components we see on that figure? It has an X-ray tube, a collimator, and the breast tissue there, as a phosphor, a scintillating material which can produce light, a fiber optic coupling, and a series of charged coupled detector arrays which are present in a slot scan mammography system. How does it work? A collimated narrow fan beam of X-rays scans synchronously across a full field of view covering the entire breast tissue. This is just a small slit which is present in the mammography system. The transmitted X-rays fall onto a thallium activated cesium iodide scintillation material to produce light. The light is channeled through optical coupling to an array of CCD cameras or detectors to form a digital image. The CCD matrix consists of 400 by 2048 pixels with a field of view of 21 into 29 centimeter, producing images that are 4 into 4 megapixels. In a slot scan system as seen, it has a curved detector plate with a resolution of 50 micron. The X-ray tube detector assembly scans from right to left, continuously acquiring a signal. A typical scan time is about 5 seconds, where the breast is immobilized using compression device. The advantage of the system is there is no anti-scatter grid for this machine. The amount of scatter is significantly reduced by the small volume of tissue irradiated at a specific time, because the slit that is present in the collimation assembly as well as on the detector assembly is small, and it leads to reduced scatter. It also leads to a significantly reduced radiation dose to the breast. However, this requires high tube loading. In these machines, tungsten can be used, or tungsten rhenium anode can be used to withstand high heating. A choice of 3 filters such as molybdenum, rhodium or aluminum is present in the slot scan scanner. Typically, higher tube voltages of 31 kVp is used compared to the molybdenum or rhodium target by these tubes. Indirect flat panel detector. Now, the basic principle is a scintillator converts X-rays to light. A photodiode array of amorphous silicon is placed in each detector element to convert light to electric charge. The electric signal is used to form a digital image. That is the basic principle of an indirect flat panel detector. In this detector, amorphous silicon diode array are constructed from a matrix of amorphous silicon thin film transistor arrays, that is TFT, which is deposited on a glass substrate as seen in this photograph. Cesium iodide scintillator material, which has higher packing factor and higher spatial resolution, are normally selected for mammography purpose. This cesium iodide scintillation detector or crystal is vapor deposited on the amorphous silicon detector array. The cesium iodide crystals grow in tiny needle shaped light pipe arrangement which resembles a fiber optic cable. It internally reflects light and minimizes light spread. It has high X-ray absorption and very high spatial resolution. The transmitted X-rays interact with cesium iodide crystal and produce light. This light is converted into charge by light sensitive amorphous silicon photodiode element which is integrated to the TFT. TFT acts like small switches. A charge collector electrode captures signal and the capacitor stores the signal. All elements are connected in a row and column matrix, and using suitable algorithms it is possible to process the image, and the image can be viewed onto high resolution monitors. In the current scenario, what we see in mammography machines for indirect flat panel detectors, a single field of view of 19 by 23 centimeter is used. It has about 100 microns detector element size, produces good contrast resolution and reasonable spatial resolution. Next, we move on to direct flat panel detector. All this while we were seeing about how indirect method is working. May it be a film screen combination or a CCD based device or an indirect flat panel detector, they use light to form an image, except in some cases where films can be used directly. When films are used directly, they have high spatial resolution. So, in case of getting high spatial resolution, it is important to manufacture a detector which can directly convert X-rays to an image. In the indirect method, X-rays have to convert to light and light into electrons. But since we have reduced spatial resolution or there is a loss because of this light conversion, we need a direct flat panel detector. We should behave like a film without a film screen, without an intensifying screen. So, what is there in the direct flat panel detector? This kind of detectors are more commonly used these days, but it is more expensive compared to the indirect flat panel detectors. In this principle, we have X-ray photons that are directly converted into electric charges within the detector. What is the detector that is used? Amorphous selenium, which is used as a direct conversion detector and is deposited directly on the thin film transistor substrate. Amorphous selenium is a semiconductor material which is placed between two electrodes. So, we are going to give power supply to these two electrodes. So, during an operation we see when high voltage is applied across the electrodes, the high voltage serves to separate electrons and holes in order to avoid recombination. As transmitted X-rays are absorbed in selenium, electron hole pairs are produced. The number of charge pairs is proportional to the incident X-ray. This charge forms the digital signal used for creating the image. Here we see an illustration, a TFT direct detection amorphous selenium TFT array, and how it is working. First, we give a bias voltage. A high voltage is given to the top electrode, and there is a dielectric layer After that, there is a selenium photoconductor. After that, we have charge collection electrode, and it has very small pixels, and that is why it determines the pixel size. After that, we have the thin film transistor, which is also having a small storage capacitor. Everything is deposited on a glass substrate. So that is a cross section of a direct flat panel detector. So X-rays here are directly converted into an electronic signal. What is the advantage of a direct flat panel detector? It has high spatial resolution, comparable to imaging detectors, very close to a film screen combination, has a field of view of approximately 25 by 29 centimeter. Pixel size can be up to 70 microns. Obviously, we need to see microcalcification, which is about 100 microns. Hence, this fits in with a 70 micron. It is possible to get a good image quality. But the limitation is large storage space per examination. When we try to image more and more, we have higher space. So this space is occupied by the picture IQL communication system. I hope you enjoyed watching this video on mammography, and let's summarize what we learned through this mammography module. What is mammography? It is a study that uses low energy X-rays for imaging the breast tissue for diagnosis and screening. The primary objective of mammography is to visualize low contrast visible mass and calcification, which may be about 100 microns in size. Molybdenum or rhodium are used as typical target material in mammography X-ray tubes. Anti-scatter grids are used in mammography. These grids have lower ratio, and the material between these strips is selected for low X-ray absorption. In traditional mammography system, non-screen cassette or non-screen films are used, or in some cases single-sided emulsion with film, with single-sided intensifying screen is used as an image detector. Films have high spatial resolution compared to other detectors used in mammography. Computer radiography uses photostimulable phosphor. These are barium fluorohalides. The image resolution may be about 50 microns. Then we move on to slot scan mammography system, which requires images using a narrow fan beam of X-rays falling on a series of CCD detectors. The indirect flat panel detector uses scintillated crystal and photodiode array of amorphous silicon to convert X-rays to light and to the electric charge to form a signal which can be viewed on a monitor. In case of a direct flat panel detector, amorphous selenium is used to convert X-rays to an electric charge. Hence, it is a direct charge. We do not have a conversion of light to electron. Hence, the digital imaging system, which is used for mammography, these days have direct flat panel detectors, which has improved spatial resolution compared to the indirect flat panel detectors. And finally, when we summarize, these are the three different types of detectors we see. One is the indirect flat panel detector, a direct flat panel detector, or a CR. This is the various digital detecting imaging systems for mammography purpose. Thank you once again.